Welcome back. Today we're going to be talking about basic combinatorics. And combinatorics is the study of how things go together. So there are different ways to arrange objects. There's different ways to pick balls out of a bag. There's different ways to roll dice, pick cards. No matter what it is, that's all combinatorics. We're going to talk about two specific cases today of looking at how is it that we can pick things, does order matter, and how ultimately do we decide what formula or approach are we going to use, and how do we determine the number of answers that there are. So let's start looking. Let me give you a framework here. This is a basic problem that you've probably been solving for a while now, since you were in grade school, middle school, thinking about outfits, okay? And so we've got to sort of use this as a springboard into talking about higher level stuff. And so when we think about this outfits problem, it's dependent on, how many things, like, can I wear two hats? Can I wear two shirts? Do I have to wear a shirt? Can I not wear a hat? And so this basic problem here, I'm going to put a couple of limitations on it. Number one, you got to pick one from each. Must pick one from each category. Okay, and I guess I could say only one, meaning that you can't put on two shirts, okay? You can't put on the shorts over the pants or two hats. And so for me, it's always helped me to sort of think about it like, okay, I've got 3 boxes here. And here's what I mean. You've got a hat, you've got a shirt, and you've got pants. And in that box is going to go the number of choices that I have, because ultimately I could take this hat and wear it with this shirt, right? And this pair of pants, that's 1. But I could also take this hat and put it with this shirt and this pair of pants, that's 2. I could take this hat, put it with this shirt, and this pair of pants, that's 3. But then I could go through and I could say, well, this hat could go with this shirt and this pair of pants, this one and this one, this one and this one. I'd have a whole lot of lines here, wouldn't I? And so there's a couple of approaches that you can use to look at this, but the easiest for me is to consider how many choices. Choice boxes. And you put the number of choices in each, and then you multiply them. You multiply them because let's say you have 5 combinations of pants and shirts. Well, then you have to multiply that by 2 because that would be the number of hats you have. So any hat could go with any of the other combinations of shirts and pants. That's why we multiply. So 2 times 3 is 6, times 2 would be 12 possible outfits. Not asking if they go together, just saying they're possible. Okay, how many possible license plates? A couple of considerations that we have to make here. Basic example. I'm going to say you can use numbers 0 through 9 and A through Z for any spot. Okay, so there's some license plates in some states where you'd have to have 3 letters and then 2 numbers or whatever, so you have specific limitations on what could go where. But if we think about it like this, we can say to ourselves, okay, I've got these slots 1, 2, 3, 4, 5, 6, 7. And if I don't have any stipulations on repeats, meaning you can't have 2 A's or you can't have 2 B's. Really, it's just a matter of multiplying 7 slots together where I have 10 options and then 26 options. So I'd have 36 times 36 times 36 times 36 times 36 times 36 times 36. So I'd have 36 to the 7th power. And that is a humongous, humongous number, okay? And my point is to say, let me rewrite it, 36 to the 7th power. My point in saying that is a humongous number, not evaluating, is there are ways that you can do this problem where you get like 200 or 300 or 400, 500 choices. Well, think about that. If you got a license plate from the state of Texas, is my answer reasonable? Is 36 to the 7th power reasonable? Yeah, I think so. Multiplication principle. That's basically what I've been teaching you. We're just putting a label on. I like to think about it in terms of my choices or my options, and you look at it in terms of boxes or bins or spots. I'm going to put a dot, dot, dot here because these are choices, the number of choices at each spot. Okay, number of choices at each spot. So that can kind of help. Okay, so let's think about this. Here's a variation of the problem. Pretty common variation where we start to eliminate repeats, or we start to stipulate what can be in what spot. Oh, you can't put a letter there. You can't put a number there. So to think about this is to really hone in on this multiplication principle. How many possible license plates if there can be no repeats in letter or number? How many spots do I have? Well, I still have 7. It has always helped me to think about this in terms of one spot at a time. I remember in college when I was taking a class on combinatorics, it was one of those things where I had to wrap my head around, don't solve the whole problem, solve it one spot at a time or one piece at a time. So think about it like this. When I first start out, if I'm picking my license plate, how many options do I have? Well, if I've got 0 through 9, that's 10, and A through Z, that's 26. So I've got 36 options for my first letter or number. Well, when I move to my next spot, if I can't have repeats, what does that mean? Well, then I'd only have 35 because no repeats. Well, then I'd have 34, then 33, then 32, then 31, and then 30. So I'd multiply all those together. It's descending because no repeats allowed. There's no repeats allowed, so my number of options decreases as I step down the line. All right, Tennessee. The Tennessee license plate consists of 3 letters of the alphabet followed by 3 numerical digits 0 through 9. Find the number of different license plates that could be formed. Common variation here. So if there is no restriction on the letters or the digits that can be used, okay, and then or goes with B. So let's think about this for a second. I've got my license plate here, 3 letters of the alphabet with no restrictions. And then 3 numerical digits. So check it out. Tennessee only has 6 characters, whereas Texas has 7 characters. Does that make a significant difference? Sure it does. Think about my first option. 3 letters of the alphabet. So that's 26 times 26 times 26. Then I'm not picking letters. So I only have 26 because it has to be a letter. My next 3 must be numbers. They must be numbers. And so we do 10 times 10 times 10. This is a case where I want to multiply this out. This one's very much smaller and see if it's reasonable. So this would be 17,576,000. Obviously, not taking into account personalized license plates or specialty license plates. This is just straight up Tennessee, 17 million license plates. All right, next variation, no letter or number can be repeated. This is a variation of the one above. And so I'm going to have 6 options, 6 ways to choose again. But I'll start with my first one. I've got 26 letters. If it can't be repeated, then it'd be 25, and then 24. Then I go to 10, because I've got 10 options for my first one, but then I can't repeat that digit, so it's 9. Then I can't repeat that digit or the one above it or the one below it, so it's times 8. Look at this. That small variation leaves me with 6 some million left. 11,232,000. So just that small variation cuts out almost 6.5 million license plates that we can use. See how that's an important distinction to make? What we've been talking about is a basic counting principle, but there's different variations of this problem. For example, let me give you paint this picture. There's a horse race, and there are 10 horses in the race. First prize, you get $5 million. Okay, so let's say they say go, and the horse race is happening and you come in second place and you miss out on $5 million. Do you care? I do. Okay? So in that case, first place matters. But let's say it's a qualifying race. And so you only have to make it into the top 3 to move on to the round where you're going to be able to race for the money. Do you care about getting first place? I mean, of course, maybe you want to win. I would. But really, I just need to get into the top 3. So whether I'm first or second or third, the order doesn't matter. However, in the championship round, the order matters. That's the difference between permutations and combinations. The best I can do is to give you a visual here. And if you think about it like an ice cream cone. As you eat an ice cream cone, generally you eat it from top to bottom, right? And so the arrangements, okay, this is arrangements, where A, B, C and C, B, A are different. What does that mean? That means that if I eat my strawberry first, then vanilla, then chocolate, that's different than chocolate, strawberry, vanilla. And maybe you don't buy into this. But when I was in college, I used to love those ice cream sandwiches that had the Neapolitan ones, chocolate, vanilla, strawberry. I always wanted to open it chocolate side first because I like chocolate the least. So I would want to eat the chocolate side first all the way down to the strawberry. And I was a little bit disappointed, honestly, if I opened up the strawberry side first and I would close it up and turn it over. Those are different ways that this could be arranged. Some examples of this would be like races, where place matters. Rank. Medals, right? So like in the Olympics, gold, silver, bronze, okay? Combinations are arrangements where CBA and ABC are the same. So I put a bowl here because you've got everything inside the bowl and you're not restricted. Like I can eat from here or there. They all kind of mix together. An example of what could possibly be combinations used for: forming groups or committees, picking top 5, no rank. Okay, so picking the top 5 students in the class, but no rank assigned. It's not like first, second, third, fourth, fifth. It's just we need 10, we need 5, or we need 8. Permutations is where the order is distinct and you're ranking things and there's a specific way they have to be arranged. Combinations is more like we have this group, you're part of the group, you're good. Here's what the formulas look like. For example, it would be n factorial. And if you don't remember what factorials are, 3 factorial is equal to 3 times 2 times 1. So whatever n is, you start with n, and in descending order, you multiply every single number or every single number after it. Okay? So when we were doing our license plate problem, this was a form of a factorial, right? So 10 times 9 times 8. So 10 factorial will be 10 times 9 times 8 times 7 times 6 times 5 times 4. Well, think about it like this. 12 horses in a race. How many ways to finish? Well, if you think about that for a second, as they're crossing the finish line, right? Cross the finish line, how many horses could come in how many horses could come in first place? Well, there could be 12. After that first horse finishes, how many options are there for second place? There's 11. Those 2 are done. How many options for third? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. as they finish, there's less options for who could come in that place, because the first place horse doesn't circle back around. It could come in 5th place also. It would be ridiculous, right? Okay, for combinations, we're going to start the same way. Let's say you've got 5 people, and you want committees of 2. How many different committees of 2 are there? Okay, it doesn't matter. Like, I'm not saying you're the number 1, you're number 2. I'm saying you got 2 people in a group, go with it. Okay, and so what happens is we start out with the same formula, because ultimately, let's think about the horse example for a second. If we're ranking them 12 times 11 times 10 times 9 times 8, down the line. But let's say for a second it didn't matter. This was a qualifying round. You just got to finish in the top 5. This is what happens in the first part of the Olympics, right? You got to be in the top 3 of your heat or whatever. For the top 3 of the heat, what I'm going to do is I'm going to divide by r factorial and then n minus r factorial. Here's what it means. This is n objects, so 12 horses, and then r at a time. Okay, I pick them r at a time, meaning I've got 12 horses, pick them 5 at a time. Well, whether I have A, B, C, D, E or B, A, C, E, D, it doesn't matter. They're all the same, right? And so I divide by this part, because this part accounts for the fact that ABC is equal to CBA. So in a combination, it's important because you're saying, I've got all these choices, but ABC and CBA are the same. So I have to eliminate that when I'm counting them. So let's work on some problems that are going to help us determine the distinction. That's sometimes the hardest part. And then apply the formulas to see what we get. Start this way. Some of the common terminology in combinatorics is words. Right, what does that mean? So by words, they're saying arrangements of letters. So it says count the number of 9-letter words. Don't worry about the dictionary meaning. It doesn't actually have to be a word. That can be formed using the letters in each word. Let's look at the word dragonfly. And so for me, this comes down to arranging all 9 letters. And how many ways can we do that? And so it's 9 bins, right? 2, 3, 4, 5, 6, 7, 8, 9. Well, think about this for a second. It's like Scrabble, right? You got all the tiles in a little bag. You pull one out. How many options did you have? Right? So you had 9. Then that one's already been used. So then how many do you have when you reach back into the bag? Times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. The shorthand way to write that is 9 factorial. Didn't say, it said arrangements of letters, doesn't talk about committees, doesn't talk about, not being repeated, because really, this is straightforward. So it's 362,880 ways. So let's look at this next problem here. The word butterfly. So when we look at the word butterfly, what are the considerations that we need to make? Think about the bins, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 bins also. 2, 3, 4, 5, 6, 7, 8, 9. And when we do this, we've got 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But think about this for a second. Let's say we had the word B-U-E-R-F-L-Y-T-T and B-U-E-R-F-L-Y-T-T. Are those the same or are they different? You can't tell, can you? Well, what if I told you I switched the T's? What if I told you I didn't switch the T's? How do you know? And so these are what are called indistinguishable objects. And so what we need to do for this one is we take ourselves our 9 factorial, and we're going to divide by 2 factorial, because 2 factorial is the number of repeated letters, 2 T's. Okay, so let's say we had another, like let's say we had, well, I guess in this next example we're going to see that, but we've got this 2 factorial because it accounts for the fact that there's repeats. And so when I do 9 factorial divided by 2 factorial, it's equal to 181,440. Okay, so you got to divide by the number of repeated letters. Okay, let's look at this word bumblebee. In the word bumblebee, again, we have 9 letters, so 9 factorial. And then here are some repeats. I got 3 B's. And so I've got to divide by 3 factorial. I also have 3 E's, so I have to divide by 3 factorial. So the numbers on the bottom that we divide by are the number of times a given element is repeated. When I do this, I get 10,080. Take a look at that. With no repeats, it's 362,000. With 1 repeated letter 1 time, it's 181,440. When I repeat 2 letters 3 times, it's 10,000. Distinguishable permutations, that's what we're talking about here. And it's n factorial over n sub 1 factorial times n sub 2 factorial dot 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 n sub k factorial. Well, what does that mean? On the bottom are given given objects of a certain kind. Okay, so in that bumblebee example, I had 2 different objects that were repeated 3 times each. Permutation counting formula is an object's take an R at a time and that would be like 26 letters in the alphabet, 3 at a time. And when they're taken 3 at a time, it's denoted NPR, or n factorial over n minus r factorial, right? So it would look like this. 26 times 25 times 24. Well, you're like, well, Mr. Saris, wouldn't it just be 26 times 25 times 24? Yes, technically. But really, the formula looks like this, and it's useful for when we have a larger number of objects or a more complicated situation. But if we think about it like this, really, it's 26 times 25 times 24 times 23 factorial, because it would be 23 times 22 times 21, all the way down. And on the bottom, we're going to divide by n minus r, so that would be 26 minus 3, right? So 23 factorial, we'll check that out. That's multiplication, it cancels out. So essentially what happens is this bin mentality that I was telling you about is I have 3 objects chosen out of a set of 26, and I don't replace them, so it's 26 times 25, 24. So then they asked me to evaluate an expression like this. 6 objects, 4 at a time. So I'd have 6 over 4 factorial. 6 minus 4 factorial, which is equal to 6 times 5 times 4 factorial. 6 times 5 times 4 times 3 times 2 times 1 over, and then 6 minus 4 would be 2, so 2 times 1. These cancel out, so I've got 6 times 5 times 4 times 3. Conceptually, 6 objects chosen 4 at a time means 4 bins, the number of choices, 6 starting, then 5 because you chose 1, 4 because you chose 2, 3. 11 objects chosen 3 at a time. 11 factorial over 11 minus 3 factorial. 11 times 10 times 9. That makes sense. There's 3 options. Times 8 factorial, and then 8 factorial on bottom. Gone, gone, done. 11 times 10 times 9. Okay, so that's the flattened out version. Let's apply this to some situations. How many ways can a chef choose 5 potatoes from a bag of 12? So think about it like this. You reach in. You got potato number 1. You got potato number 2. If you're going to put them in a pot, does it matter? Are we ranking them? No, they're not ranked. Not a rank. Okay, we're just choosing a group of 5. This is a group. So is this permutations? We'll look up here. Permutations is where we had ranks and medals, and races where place matters. Combinations were committees or groups. And so this, we're going to use our NCR formula. And we're going to have 12 potatoes chosen 5 at a time. So I'm going to have 12 factorial, and then I have to eliminate the repeats because potato A, B, C, D, E is the same as potato D, C, A, B, E. I think I got all letters right. Okay? And so it's going to be over 5 factorial and then 7 factorial. So it's equal to 12 times 11 times 10 times 9 times 8 over 5 factorial. Okay? And that's the way that I'm going to do that. But the hardest part of this one is distinguishing exactly what in the world am I going to be using. And so that's a combination formula. How many ways can the 10 finalists be chosen from the field of 51 in the Miss America pageant? It's asking for finalists. It's not asking how many ways can they finish. This one's tricky, right? And so I'm really going to have 51 ladies, and I'm going to choose them 10 at a time. But it doesn't matter. If you've got, you know, Alabama, Texas, Missouri, if in the 10 finalists, you know, it doesn't matter what order they came in, they're just picking 10. 51 factorial over 10 factorial, that's my number of options, and then 41 factorial, that eliminates the rest, the tail, right? So that eliminates everybody who didn't get chosen, okay? This one's the trickiest of them all so far. The Georgia Lotto requires winners to pick 6 integers between 1 and 46. The order that they are in does not matter. Indeed, the lottery tickets are always printed in ascending order and the numbers are not repeated. So, if I've got 1, 2, 3, 4, 5, 6, the guy next to me picks 6, 5, 4, 3, 2, 1. When it prints out, they're automatically going to put them in ascending order. So, when we do this, think about literally these lotto balls. They put them in like 6 different machines, or they might put them in the same machine depending on how they do this. This one seems to say they've got the balls, they're in one machine. And so there's 46 options to begin with, then 45, then 44, then 43, then 42, then 41. But I have to eliminate the repeats. And so I've got to divide by 6 factorial because I'm saying I've got everything the same. If it's 1 through 6, it's 1 through 6, no matter what order I put them in. And so another way to think of this, so if you're a formulas person, you might say I've got 46 and I'm going to choose 6 of them. Okay? And that would be 9,366,819. I've always thought to myself, why wouldn't I just buy every lotto ticket? Well, I got to evaluate, is the winning going to be worth it, right? Okay. Armato's Pizzeria offers patrons any combination of toppings, up to 10 different toppings. Pepperoni, mushroom, sausage, onion, green pepper, bacon, prosciutto, black olive, green olive, and anchovies. How many different pizzas can be ordered if you choose any 3 toppings? Once the olives are on there, they're on there. It doesn't matter if you put them on first, second, third, last. That is 10 toppings, choose 3. And that's going to be equal to 10 factorial over 3 factorial, 7 factorial is equal to 120. There's only 120 pizzas that you can choose with 3 toppings. However, if I could put 10 toppings on, think about it like this. I have 10 choices to make. 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is a yes or a no, a yes or a no, a yes or a no, etc. So in each bin now, I'm making 10 choices. You're going down the line and you are telling them what you want on the pizza. But essentially, if you tell them pepperoni, mushroom, and sausage, nothing else, then you said no to 7 other things. You really have 10 choices, right? Do I put it on or not? And so I've got 2 to the 10th power here, right? So it would be 2 to the n. You could do this with anything, with any number of pizza toppings, right? So that's a 2 to the n formula, right? So any number of subsets. So a subset would be you pick 6 out of the 10, and the order doesn't matter. That's going to be a 2 to the n. N is the number of or no options. That's the way that I like to think about it, right? Okay, there's 16 actors answering a casting call for a production of Snow White and the Seven Dwarfs. How many ways can the director cast the 7 parts? So, is it rank? Is it not rank? Let's think about it like this. He's casting parts. So if I go in for the role of Dopey, and I get the role of Dopey, is that different than me getting the role of Grumpy? Yeah, it very much is. And so for this one, order matters like rank. And so this is 16 people. 7 at a time is 16 times 15 times 14 times 13 times 12 times 11 times 10. 1, 2, 3, 4, 5, 6, 7 is equal to, some of the notes here, calculator. Is this awkward silence? Insert, so I'm actually going to use 16 permutations, 7 at a time. Whoa, wowzers. 576, nope, 5,760,000, no, 57,657,600. Put my zeros in and then put my commas in, all right? 57 million ways to cast these 16 actors as the 7 dwarfs because it's a different experience if I'm Dopey or Doc or Bashful or Sleepy or Grumpy or I can't remember the rest, okay? That's permutations and combinations. Permutations and combinations are combinatorics. How do we combine things? Does order matter or doesn't? If you have any questions, guys, let me know, and thanks for watching.